now that you guys have learned how to draw the orbital diagram for elements when given their electron configuration, one last concept that I need to introduce is the concept of paramagnetism and diamagnetism. Now, if an element is paramagnetic, what that means is that one or more of its electrons are unpaired. So when you draw the orbital diagram, the element has one or more unpaired electrons. And as a result of these unpaired electrons, those elements are going to be attracted to an external magnetic field. And so here are some examples of paramagnetic elements. As you can see from their orbital diagrams, for example, aluminum has one unpaired electron, silicon has 2, phosphorus has 3, and sulfur has 2. Now, if an element is diamagnetic, what that means is that all of its electrons are paired, and as a result, elements that are diamagnetic are not going to be attracted to an external magnetic field. And so examples of these, anything that has a full orbital. So for example, if the 2p orbital were filled, or if the d orbital were completely filled so it does not have any unpaired electrons. So that's paramagnetic and diamagnetic. It's a really nice laboratory technique. It can help us to identify an element based on whether we anticipate it being paramagnetic and diamagnetic based on its orbital diagram. The next concept I'm going to introduce is Coulomb's law. Now, here's the formula for Coulomb's law, and notice Coulomb's law is talking about the force, and it's the force of attraction. And so what it tells you is that the force equals K, which is a constant, times Q1, Q2. Now, Q is the magnitude of the charges that you're dealing with. So for example, if you have a +2 charge, the magnitude of the charge would be a 2. If it's +3, it would be 3. If it was -2, it would be 2 as well. And then D, which represents the distance between the nuclei. And so just by using this equation, what we can determine is that the larger the magnitude of the charge, the larger the force. The smaller the distance between the nuclei, the larger the force. And so that helps us in determining strengths of ionic bonds and being able to predict which ionic bonds will be strongest. And so here are the rules just reviewed for you based on Coulomb's law. The larger the charge and the shorter the distance between the nuclei of two atoms, the stronger the ionic bond is going to be. And so for example, if we were to compare calcium oxide, magnesium oxide, and sodium oxide, if we were first to compare calcium oxide and magnesium oxide, if you notice, magnesium is a smaller atom than calcium, and so as a result, since that's the only difference between those two because they have the same charge, magnesium oxide is going to have a stronger ionic bond because the distance between the nuclei is going to be shorter because magnesium is smaller than calcium. One way of measuring the strength of an ionic bond is actually measuring its melting point. So the stronger an ionic bond is, the higher its melting point is going to be, the higher the temperature required to actually melt it. And so as a result, magnesium oxide is going to have a much higher melting point than calcium oxide. Now if we compare calcium oxide and sodium oxide, the main difference between calcium oxide and sodium oxide is the fact that sodium only has a +1 charge. And so since its charge is less than that of calcium, which is 2, I know that the ionic bond between sodium and oxygen is going to be weaker than that between calcium and oxygen. And so as a result, if I were asked which would have a higher melting point, I know that calcium oxide would have a higher melting point because it has a stronger ionic bond. The next concept we're going to be talking about is the size of atoms. Now quickly, as a definition, the size of an atom is defined as the distance between the two nuclei. Because it is so hard to determine exactly where an electron is, it's impossible to measure the radius or the size of an atom based on the distance between the nucleus and the outermost electron. So instead what we do is we measure the distance between two nuclei. So as far as size is concerned, as you move down a group, the size of an atom increases. Now it increases because as you move down the periodic table, you increase the number of energy levels. And therefore, as you increase the number of energy levels, the size of the atom is going to increase. Now, as you move across the periodic table, what happens is that the size of an atom decreases. Now, this is because the number of protons as you move across the periodic table increases. Another name for this is the effective nuclear charge. The effective nuclear charge is the attraction from the nucleus that electrons actually experience. So because the number of protons increases, but you're not increasing energy levels because you're not moving down, the electrons experience more of that positive nuclear charge and therefore are going to be pulled towards the center, and therefore the size of the atom is going to decrease. So here's a really nice way of looking at it. As you know, if you look at group 1, as you move down the periodic table, the size of the atoms gets larger like we predicted, and that's because you have more and more energy levels. Hydrogen only has the first principal energy level, lithium has the first and the second, sodium has the first, second, and the third, and so you're just increasing in size. As you move across the periodic table, effective nuclear charge increases, and therefore the electrons are going to be attracted to the nucleus and therefore brought in, so the size of the atom decreases. Now, so far we've been talking about atoms. Well, what about ions? Well, if you have a cation, meaning a positively charged ion, the way you got that cation was by removing an electron. By removing an electron, you actually decrease the size, so cations are smaller than their parent ions, and that's because they have fewer electrons. Now, electrons are going to repel one another, so the fewer electrons you have, the fewer repulsions you have, and therefore it's going to be much more neat and tidy, and the electrons are going to be pulled towards the nucleus. Now, if you have an anion, anions are going to be larger than their parent atoms, and that's because you have more electrons and therefore you have more repulsions. If you look at the oxide ion, fluoride ion, sodium ion, the magnesium ion, and the aluminum ion that I've given you, it says that they're isoelectronic, meaning you have the same number of electrons. So it wants us to list these in order of increasing size. Well, aluminum has the most protons, therefore it has the largest effective nuclear charge. And since they all have the same number of electrons, aluminum is going to be the smallest, followed by magnesium, followed by sodium, followed by fluorine, which is much bigger, the fluoride ion, followed by oxide. Another characteristic of atoms is their ionization energy. And when we're discussing ionization energy, we're going to be talking about the size of the atom, which we just went over. The ionization energy is the minimum energy required to remove an electron. And so if we think about it, as you move down a group, the number of principal energy levels increases. And so as a result, the effective nuclear charge, the attraction that the nucleus has for electrons, that's going to decrease because you have more and more electrons between the electron you're trying to remove and the nucleus. Now, this phenomena is called the shielding effect. And so the shielding effect is simply a reduction of nuclear attraction for the electrons. So if you look right here, if you compare magnesium and calcium, notice calcium has a whole nother principal energy level above that of magnesium. Therefore, calcium is going to have more shielding occur, meaning that those two electrons in that outer energy level are not going to experience the attraction of the nucleus as much as those for magnesium. Therefore, calcium has a lower effective nuclear charge, meaning it is easier to remove those two outermost electrons. Now, as you move across the periodic table, we know that the effective nuclear charge increases. And so as a result, since the effective nuclear charge increases, and not to mention the fact that the electron is closer to the nucleus, those kind of are tied together, the energy required to remove an electron increases. So as you move down a group, the size of your atom increases because you have more principal energy levels, and due to the shielding effect, the attraction the nucleus has for the electrons is going to be less, and therefore the ionization energy is going to decrease. In contrast, as you move across the periodic table, because there's a greater effective nuclear charge, and because that electron is closer to the nucleus, the ionization energy is going to increase. The last concept we're going to go over is successive ionization energies. There isn't just one ionization energy. Instead, with each electron that you remove, there is an ionization energy that goes along with that. And as you would expect, if you look first and compare simply I1, which is the first ionization energy, and I2, there is an increase, and that should be expected because if you think about it, if you remove one electron, to remove another electron, you're getting rid of an electron, which means that the nucleus is going to be more effective at attracting more electrons. So it should increase with each ionization energy. What shouldn't happen, as you can see, is these sudden huge jumps in ionization energy. For sodium, it's between I1 and I2. For magnesium, between the second and the third ionization energy. We expect an increase. That makes sense as an atom becomes more and more and more positive. Okay, but why is there such a huge increase? And that's because if you look at the periodic table and consider the electron configuration of sodium, sodium is 1s2, 2s2, 2p6, 3s1. If you remove that first electron, that's in the outer shell of electrons, and therefore it's going to be easier to remove because it's farther away from the nucleus. It has a lower effective nuclear charge, and therefore it's very easy to remove that electron. Now, if I try, after I remove that first electron, if I go and try and remove a second electron, at that point I'm removing electrons from the inner shell of electrons, which experience more attraction to the nucleus, are closer to the nucleus, and therefore it's going to be a lot harder to do. And so if you notice from I1 to I2, there's a huge jump in ionization energies. Now, just to make sure we're clear on this, if you look at magnesium, notice the first ionization energy and the second ionization energy are not, there's not a huge difference, there isn't a big leap. But then going from the second ionization energy to the third ionization energy, there is a big leap in ionization energies. And that's because in order to remove those first two electrons, those are from the outer shell, and therefore they're not experiencing as much attraction. They're farther away from the nucleus, they're fine. But as soon as you start trying to remove electrons from the inner shell, the 2p, that's going to require quite a bit more energy, and in fact almost 7 times as much energy as it was to remove that second electron. And so as a result, as you can see, ionization energies will increase as you remove the first, the second, the third, but then you're going to have big jumps as you start removing electrons from the inner shell of electrons.